have to take this factor and multiply by n, and I get this root n speedup, as was pointed out in this very well-known work from Lucan and others in 2001. So the light atom coupling is enhanced by a factor square root of the number of atoms. It's collective enhancement of the light atom interaction. And as we'll hear more about this week, this is crucial for getting very strong interactions at the single photon level. For a number of reasons, it's of interest to try and use not single atoms for quantum computation, but to use qubits defined with n atoms. This has some advantages in terms of enhanced light atom interaction. It also has advantages if we have difficulty in preparing single atom states and can more easily prepare traps with some n greater than 1 in each one of those traps. So there's interest in trying to do coherent oscillations, perform coherent oscillations on these n atom states. So here's some data from our group in Madison showing the coherent oscillations between the ground and a singly excited state, which we then map down onto another ground state to measure for a deterministically prepared single atom in the trap. So this is just ground, Rydberg, ground. And then for an average number of atoms with the loading statistics being Poissonian, ranging up to about 15. And this is work done by Matt Ebert, who's here, and we have a poster that you can see later in the week, which has more details about these measurements. But what we're able to do here is compare the average, or compare the Rabi frequency of the collective oscillations with the number of atoms. And the number of atoms we measure using a different technique, using light scattering from the ensemble, corrected for the loss of atoms due to light-assisted collisions. So we have a comparison between theory, the root n theory, and the measured frequency with no adjustable parameters, just a straight theoretical fit. And indeed, you see a very good correspondence between the measured number of atoms and the expected Rabi oscillation frequency. You also see, as you increase the number of atoms, that the oscillations are washing out. They're reducing in amplitude, and they're also dephasing. And this is due to the fact that we're averaging over a Poisson distribution. Each one of these data points is acquired by repeating the experiment some number of times and finding the average value at this, the average excitation value at this value of the pulse length. And because we're averaging over states with different numbers n in them, because our loading is Poissonian, we have to average over the root n factor. And since we don't know n a priori, it's Poisson distributed, that averaging leads to a dephasing of these curves. So these solid lines here are, again, the expected average oscillations averaging over a Poisson distribution. And they indeed agree quite well with the measured data. But if we want to use ensembles within atoms for quantum bits, then this dephasing is a problem, since we don't, in general, know n a priori. So what can we do about that? Well, one possible solution is to use adiabatic passages. And so stirrup-stimulated Raman adiabatic passage is a very well-known technique in atomic physics. There's a lot of literature on this. One very good review article is this work by Bergman et al. From 1998. And one of the basic techniques called stirrup uses a two-photon excitation, but in a counterintuitive pulse sequence. So I'm going from the ground state up to the Rydberg state via this intermediate P state, and I apply the second photon first, followed by a pulse with the first photon. So I apply this frequency first, followed by this lower frequency. So initially, if the atoms are starting in the ground state, this light S here doesn't do anything. In the ground state, this is coupling these two levels, has very little effect. But if I apply these two pulses in this counterintuitive sequence, and they're smoothly varying pulses, what happens is there's a transfer from the ground to the excited state via a dark state, which contains no component of P. So in principle, one can do complete transfer from G to R without ever exciting P. That gets rid of spontaneous emission. I have no spontaneous emission. And also the probability of ending up in the state R becomes very insensitive to the actual value of the Rabi frequency. And that means I can become insensitive to this root n variation. So that's very nice. This technique is very well known for transitions between different ground states or low-lying excited states, but within the past decade has also been used for Rydberg state excitation. I think that was the first time in the rifle group in about 2005, where they looked at the coherent population transfer of ground state atoms into Rydberg states using this stirrup type sequence. They actually didn't use these Gaussian envelopes like you see here. They used kind of square envelopes, partially overlapping. The precise form of the envelope turns out to be not that important. And they came up with a very nice method of using a double sequence. So first one sequence, then a second sequence, which allowed them to extract the quantitative efficiency of the excitation, even though they didn't know the original number of atoms they were interacting with. So they did this for a couple different pulse lengths of the sequences and saw excitation efficiency getting up to about 70%. And you don't see, so you can sort of see some of the time domain behavior here. There's kind of a relatively flat excitation efficiency as they vary here the time between the pulses, the partial overlap of these pulses. So this is in a many atom sample, again about 70% efficiency. We've recently been looking at this in our lab. And with single atoms, we're now able to get close to 100% for single atoms using stirrup pulses. So this is a rubidium, a 780, 480. This is the pulse timing. We turn on the blue light first. Since the first part of that Gaussian blue pulse really doesn't do anything, we just start with the blue pulse high. So we decrease that, and as the blue pulse is decreasing, we then start turning on the red pulse, the 780 pulse. It stays on for some time, and then to make a measurement, we then end with a short pulse of blue light to couple any Rydberg population back to the 5p, so it's spontaneously the case. And here you see the measured ground state population. We start in the ground state, we have this excitation, and the point is that we have a very flat region of the curve here. We have essentially constant Rydberg excitation, even though the pulse length is variable, and so that would correspond to the pulse length being fixed and having a variable number of atoms, giving us a variable root n omega frequency. So for one atom, this is working very well. For many atoms, we're right now at about 60% efficiency, but this is something that we're actively working on and trying to understand why it's 60% and not something close to 100%. So that looks interesting for exciting many atom samples without having previous knowledge of the number of atoms. However, there's some surprises. These adiabatic pulses have a very rich physics. If the Rydberg atoms are non-interacting, 100% transfer from ground state to Rydberg state is theoretically possible. When the atoms are Rydberg blockaded, that is, they're strongly interacting, we can only excite one Rydberg atom at a time, it turns out that stirrup will transfer 0 or 1 atom depending on whether the number of atoms we start with is even or odd. This is something that was discovered by Klaus Mulmer about 5 years ago. So in a strongly blockaded ensemble, strongly interacting ensemble, doing a stirrup excitation sequence will give you a 0 or 1 atom excited, will give you a parity measurement event, which is kind of interesting. There's not, I don't know of many other ways of getting that parity measurement apart from directly counting the number of atoms, okay? So that's nice, and in fact, you can do some interesting quantum gates and create multi-particle entanglement using this method, which is sort of the main topic of this paper. But if I think about using stirrup to perform pulses on my multi-atom qubits, then this is a problem and not a feature, because it means that the stirrup is no longer going to work. If I have an ensemble with, say, 10 or 11 atoms, then I'll either get a perfect pulse, 1 atom excitation, or get no excitation. So this implies that the stirrup pulses are not going to work well on my ensembles. So that's going to be a problem. What can we do about that? Well, it turns out if one does stirrup in a slightly different way, it will work. So this is the Mulmer paper where we have this 2-photon stirrup, which is resonant at the P level. this will transfer 0 or 1 atom to the Rydberg state. And here I don't have time to go into the details of exactly why that is, but the dark state in this situation is either 0 or 1 atom depending on the parity of that. If instead we make a slight modification and detune the lasers from the intermediate level by an amount delta, which is large compared to the Rabi frequencies, then the stirrup will always give us 1 atom excitation, irrespective of the parity event. So this was pointed out by the Novosibirsk group a couple years later. So this suggests that we can indeed use stirrup for single atom excitation. We just need to detune from it. Okay. So that sounds good, except there's still a problem lurking. So here's a picture showing you the improvement. This shows the pi pulse error, so that is the error in exciting a single atom in a strongly interacting sample as a function of the number of atoms I'm starting with. If I use Rabi rotations, that is just square pulses of well-defined period, then if I set up my pulse period such that root n omega times time is a pi pulse for 5 atoms, then I have 0 error for 5 atoms. But as I move away from 5 atoms, the error grows very rapidly. So a Poisson distribution centered at 5 would have substantial population in the close neighbors, and I'd get substantial errors in my Rydberg excitation. If we instead use stirrup, or another kind of adiabatic pulse called adiabatic rapid passage, where I sweep the frequency of the photon across the resonance, either that or stirrup, I can greatly reduce the error and be largely insensitive to the number of atoms. So, and this reduction in the error is several orders of magnitude. So that looks like a good improvement. However, there's still an issue lurking, which is phase sensitivity. I started out by saying to perform quantum gates using these Rydberg interactions, we need good control of not just the amplitude, but also the phase of the wave function for both the ground states and Rydberg states. And although these adiabatic pulses, either stirrup or arc, give very good control of the amplitude of the pulse without knowing the number of atoms, there's a phase uncertainty that comes in. And you see that here. This is the phase of the wave function after a double stirrup pulse where I start in the ground state, go up to the Rydberg state, and back down. And so for 1 atom, I go up and I come back down. If I increase the number of atoms, because the 1 photon Rabi frequencies are very high, there's this very rapid phase oscillation, and I end up with a phase on the wave function which changes rapidly with the number of atoms. So although the amplitude for the Rydberg excitation and de-excitation can be well defined, the actual phase of the wave function, which is what I care about for gates and creating entanglement, becomes very sensitive to the number of atoms. So that's again a problem, and we need to do something about that. It turns out you can compensate this phase using some more complicated pulses. So if I look at a double pulse sequence that takes me from the ground state up to a Rydberg state and back, and I change the sign of this detuning between the first and the second pulse pair, it turns out changing the sign of that detuning will cancel this phase sensitivity. Similarly, for these adiabatic rapid passage pulses, where one sweeps across the resonance, if one changes the phase of the field in between the 2 pulses, that will also compensate this phase sensitivity. But this was an idea that came out of the Novosibirsk group. And here you see some numerical calculations using stirrup with no phase compensation, showing this large phase sensitivity of the wave function to the number of atoms, going from 1 up to 7. Here for compensated stirrup pulses, and here for these adiabatic rapid passage pulses also works very well to cancel this phase sensitivity. So this has not been demonstrated yet, but we're hopeful that this is going to be an avenue towards using ensemble qubits for well-defined quantum gates. And indeed, you can take those pulses and translate them into protocols for single qubit gates and entangling C0 gates on ensemble qubits. I'll come back and explain this in more detail in the third lecture. So let me summarize there. I'm a little bit early, that's probably good. Get to lunch. And I've told you about excitation Rydberg stage, which can be performed coherently with modern stabilized laser sources, provided one pays good attention to issues associated with Doppler broadening, AC Stark shifts, and state selection in both the ground and the Rydberg manifolds. I've concentrated on the simplest cases of constant in time linear excitation, but when we go to these ensemble qubits, where we get a root n speed up, then the use of temporally modulated sequences such as stirrup allow for full amplitude and phase control. So indeed, using the tools of quantum optics, it appears there are ways of accurately controlling these many atom qubits, not just single atom qubits. And I'll stop there. Thanks.
Thank you. Questions?